Irrotational flows have some special properties which render the equations governing them linear, and therefore these flows have been studied in great details. Before doing this, we introduced the concept of vortex lines and circulation. These two concepts play very important role in irrotational flows. A vortex line is defined just like a streamline. It is a line which is tangent to the vorticity vector. The vorticity vector is omega is equal to curl V, and at every point the vorticity vector is tangent to a vortex line. A vortex tube is a bundle of vortex line passing through a closed circuit C. Imagine a circuit C as shown. From every point of this, we pass a vortex line, and so this vortex line would occupy a tubular region in space, and this tubular region is termed as a vortex tube. We shall later see that an important property of vortex tube is that a vortex tube either closes on itself or extends to the boundaries of the flow. Here we have shown a smoke ring gun. It is made of a container in which smoke is filled, and there is a diaphragm at the back where we tap and a smoke ring comes out. The smoke rings are regions of vorticity, donut shaped vortex tube. Shown in the right is the pattern of the flow in these. If we take the central axis of this donut, we see that there is a vorticity vector tangent to it at every point. The strength of the vortex tube is defined by the product of the vorticity normal to the surface enclosed by the curve C. So in this curve C, if we take a small area dA, then the strength of the vortex tube is the integral over the capping area of omega, capital omega times dA, where capital omega is the vorticity vector, curl of V. Thus, the vortex tube strength is equal to the normal component of vorticity integrated over the area of cross section of the vortex tube. Some texts make a mistake and describe this vortex strength omega dot dA as the flux of vorticity through the tube. It is wrong in the sense that this vorticity is not flowing through the tube. It does not flow through the tube. So there is no flux. It does not enter the tube. Those of you who are familiar with the calculus of vectors know that Gauss's theorem relates the integral of a vector quantity over a closed circuit to the surface integral of the curl of that quantity over a surface capping the circuit. Thus, for the vortex tube shown, the strength of the vortex, which is the integral of curl V times dA over the area capping C, is equal to the line integral over the closed circuit C of V dot ds. That becomes the tangential component of velocity along the circuit. Thus, the strength of the vortex tube is equal to the integral of the tangential component of the velocity around a circuit enclosing the tube. This is interesting development because there is a name for this integral over the closed circuit, and that name is circulation. Integral V dot ds over a closed circuit C is termed as the circulation gamma, with the integration proceeding in the counterclockwise direction. The circulation about a circuit equals to the vortex strength of the vortex tube formed by the vortex lines passing through each point of the circuit. So we start with the circuit C, then the circulation about the circuit C is equal to the vortex strength of the vortex tube formed by the vortex lines passing through each point of the circuit. Another important property of vorticity is that there is no component of vorticity through a closed surface. That is, if capital omega is the vorticity vector at any point, then omega dot dA integrated over a closed surface, a surface enclosing a volume, is 0 if the flow is rotational. And for this, we require the divergence theorem from the calculus of vectors. The divergence theorem states that if we consider a volume V bound by a closed surface S, then the integral over the bounding surface of curl V dot dA is integral over the volume of the divergence of curl V dV. The right hand side of this expression vanishes since the divergence of curl must be 0. Curl is perpendicular to the divergence vector, and so divergence of curl must be 0 identically, and therefore we get the net component of vorticity through a closed surface as 0. We'll use these facts shortly. Now, one of the important properties of vortex tubes is that the circulation is same in all circuits embracing the same vortex tube. Consider a volume which is part of a vortex tube shown. The enclosing surface of this volume is broken up into 3 parts, 1 and 2 as the cross section of the vortex tube, and third is a surface of the vortex tube itself. So surfaces 1, 2 and 3 enclose a part of the vortex tube. Now, the net vorticity at the surface through the closed surface must be 0. Since the surface 3, which is tangential to the vortex tube, is a vortex surface in the sense that the vortex vector is parallel to these, tangent at every point of the surface. So the vorticity through this surface is 0. So V vortex dot dA, vorticity dot dA over surface 1 must equal the vorticity dot dA integrated over the surface 2. That is, the net component of vorticity across each cross section is the same in inward at one and the outward at other. And since this normal component of vorticity is the strength of the vortex tube, and the strength of the vortex tube is the circulation. So the circulation is the same for all circuits embracing the same vortex tube. In other words, the strength of the vortex tube remains constant along its length. And if this be so, this implies that a vortex tube cannot terminate within an inviscid fluid. Thus, if I have a vortex tube, it cannot end within an inviscid fluid, because what happens to the vorticity after that? So, it must either close on itself like a vortex ring or extend to the boundaries of the flow. After persisting for a while, a smoke ring diffuses away. This is because of the viscous action over time. Another example of vortex tube ending on itself is the vortex pattern on an aircraft wing, which forms a complete circuit consisting of a U-shaped vortex and the starting vortex left at the airport. This is a typical pattern of vortices on an aircraft wing. We assume a bound vortex on the wing. In fact, it is this vorticity that is supposed to produce the lift. The Prandtl's theory of aircraft wings is based on this assumption that there is a bound vortex with the wing. There are two trailing vortices and a starting vortex. I'll show a little bit later the development of the starting vortex. But then this bound vortex in two longitudinal vortex, which are called the trailing vortex, and this starting vortex form a closed loop of vorticity, of vortex tubes. This picture shows the vorticity trailing from the edges of the aircraft wing. Another view of these trailing vortices, we are looking behind the aircraft and the smoke is swirling around, showing two distinct vortices at the two wingtips. And there is a starting vortex. As the aircraft wing moves, a vortex is formed which is bound with the wing, and there is a vortex which is termed as a starting vortex and is left behind at the airfield. Further properties of vortex tubes. The relationship between circulation and the area integral of the vorticity is only valid if the region enclosed by the contour C is simply connected. This means that the region must be such that it is possible to shrink the contour C to a point without leaving the region. So a region with a hole like a bathtub drain is not simply connected, since any contour that we take around it cannot shrink to a point. The bathtub drain would come in between. Similarly, a flow about a two-dimensional body is not simply connected. This circuit C shown here cannot shrink to a point. The presence of this yellow body would forbid that. Of course, this is possible only in two dimensions. In three dimensions, if the yellow body was a three-dimensional body, we could have a capping surface on C which avoids the solid body. And this contour could shrink along the capping surface. Another property, the circulation about any circuit enclosing a 2D body within an irrotational flow is the same. This is easy to show. Consider a two body and two circuits C1 and C2. Neither C1 nor C2 can be shrunk to a point, but we can artificially create a composite circuit, slit the space between the two circuits by two straight lines L1 and L2 and connect them to C1 and C2 in the manner shown. Now, the circuit which consists of L1, C2, L2 and C1 is a circuit which is reducible and which lies totally within an inviscid flow. We can shrink this to a point, and that point would lie within the inviscid flow. It avoids the 2D body completely. And so the circulation about this should be zero, since this lies wholly within the inviscid flow. There is no vorticity which is enclosed. Now, the circulation produced by the component L1 and L2 cancel out because they are in the opposite direction. So, this shows that the circulation about C1 and about C2 must be the same. Circulation about a circuit that lies within inviscid flow is the same for all circuits going around a 2D body. There's a famous theorem called Kelvin circulation theorem. We will not prove it here because it takes a little higher level of vector calculus, but the theorem is easy to understand. The circulation around any material loop in an inviscid and incompressible fluid does not change with time. Consider this circuit as a material loop. This is the position at a given time t. At a time t plus t, the same particles occupy this new location. These are the same material particles. So we say the circuit is a material circuit. Then whatever be the circulation of this loop, of this circuit, at any given time remains constant with time. d gamma by dt is 0. Note that this being a material circuit is important. And this gives an interesting conclusion. Consider an aerofoil sitting in an inviscid fluid. There is no velocity anywhere. I draw a circuit C. Clearly, since the velocity is zero, the circulation around this circuit is zero. Now let us assume that the fluid starts moving to the right. As the fluid starts moving to the right, this circuit would stretch and would occupy a position like this. I replaced that aerofoil by a picture, a photograph that was originally produced by Prandtl himself in his laboratory. And in this photograph, you see a vortex out here. So there is vorticity now that is induced there. The science of aerodynamics as developed by Prandtl talks about the origin of this vortex, which is termed as the starting vortex, which you talked about earlier. Now, the circulation about this white circuit that we've shown here would still be zero because it's the material circuit. So how about this vorticity? Divide the circuit into two circuits, C1 and C2. The original circuit C was nothing but C1 plus C2. The contribution to circulation about these two arms cancel one another out. They are close together. Around circuit C2, there is a positive circulation because the flow around the starting vortex is counterclockwise. So there is a positive C2. Now, about the circuit C1, then there should be an equal and opposite circulation because the net circulation must still be zero. This circulation is due to what is termed as the bound vortex with the wing. So the wing has a circulation going clockwise. This is the bound vortex, which is one arm of the closed vortex circuit behind an aircraft wing. Imagine a circuit on the vortex surface. Since the vorticity on the vortex surface is tangential to the surface, the circulation about this circuit is zero. If we follow the material that constitutes this circuit, the circulation about it is always zero by Kelvin theorem. This is true for any circuit on the vortex surface. Thus, the vortex surface is a material surface. So whatever is a vortex surface once will always be a vortex surface in an irrotational flow. Since the surface of a vortex tube is a vortex surface, a vortex tube is a material tube, always constituted by the same material particle. Thus, a smoke ring, a vortex tube closing on itself, is a material tube. That's why we see as a tube of smoke, the same smoke always. The intersection of two vortex surfaces is a vortex line, and it follows from the above that this too should be a material structure. Thus, a vortex line is a material line. For the special case of a vortex tube with small area, the vorticity omega can be considered as approximately uniform across the tube cross section A, and the strength of the vortex tube can be written as gamma is equal to omega times A. Therefore, if we stretch the vortex tube, and since it is a material tube, it consists of the same material. If we stretch it, its cross-sectional area will decrease, and so this vorticity along a vortex tube varies inversely as the cross-sectional area of the tube. This clip shows a ballerina. The ballerina is spinning around, and as she stretches herself by raising her hands, the speed of rotation goes up. That's exactly how the vorticity along a stream tube increases. This has been illustrated very nicely by Professor Shapiro of MIT in a movie, Vorticity 2, produced by him for the National Committee of Fluid Mechanics film in 1964.
To show the effect of stretching vortex lines, we have an apparatus in which water flows over a hump. The water depth first decreases and then increases. The speed of the water is inversely proportional to the depth, and so the flow accelerates as it goes up the hump and then decelerates as it goes down the hump. Now I'm making a vortex with a sharp-edged plate. This vortex has its axis vertical. As it goes up the hump, the length of the vertical vortex line decreases, and so the vorticity decreases, as you can see by the spin. When the vortex line goes down the hump, the length of the line increases, and the rate of spin also increases.
Thank you very much.